What is up, math rock stars? We've got section 4.5, day 1. This is rational functions. What's a rational function? A rational is the same thing as ratio. That's the base word. And then ratio is kind of the same thing as fraction. So all of these functions have fractions. We're basically putting polynomials into fractions and seeing what comes out. Fraction, fraction, fraction. They're all fractions. You get these really crazy curves that have these, they get broken up because as you can see here, there cannot be a 0 in the denominator. So you can see x such that x is not equal to 0 is what the function would have to be. That's the domain. The domain here is from negative infinity to 0, and then combine that with from 0 to infinity, leaving out 0. All real numbers except for 0. That's what the domain is. Here, we've got the set notation of x should not equal to 0, and then from negative infinity to 0, with the union of 0 to infinity. So you can see here, each one of these interval notations represents another part of this graph. So you can see in this version, we've got three different, when you factor it, you've got two places where x cannot equal in the domain -2 and +1. So when you have these two different breaks, it breaks up the whole graph into three different parts. Here's the first part, negative infinity to -2, and then the middle interval here, -2 to 1, and then the final interval, 1 to positive infinity. Three different intervals, three different parts of the graph, broken up by two different places in the domain where x cannot equal, two different values. So we can see here, these dotted lines we're going to give a name to, and they're going to be called asymptotes. That's right, if you skip down to the next page, we're going to call them asymptotes. And you might as well start drawing them in now, because these lines are vertical lines, and this vertical line is at x equals 1, and this vertical line is at x equals -2. Here we see, because we want to know where 2x minus 6 equals 0, that would be where the denominator equals 0. We solve that, we can find that x equals 3. So if you draw a vertical line at x equals +3, that's the place where the graph gets broken up into two different parts. The domain is all x such that x does not equal to 3. And if you write that in interval notation, it's from negative infinity to 3 and from 3 to infinity. Here we can factor the denominator, and we get x plus 1 and x minus 2. And after factoring the denominator, if we set it equal to 0, then we see that x cannot equal to -1 and +2. So if that's true, then the set notation would look like this. The interval notation would go from negative infinity to -1, that's here. In between -1 and 2, that's here. And then also 2 to infinity, that's here. Never touching -1, never touching +2. One more strange one right here. We've got x squared and x plus 1. I say it's strange because it's making these kind of sideways parabolas. Anyway, x plus 1 here dictates that x should never equal -1. You have to remove -1 from the domain, and that's how you write it with set notation and interval notation. You can see there's a vertical line here at x equals -1 that the graph will never touch. So, without even looking at the graph, you could even just do the domain right here, just making sure that x is never equal to 3. That's what the set notation would look like. I want you, right now, to figure out what the interval notation looks like. Pause the video, and then when you're finished, we can resume. So, as I alluded to before, here are asymptotes. Asymptotes are lines that graphs will never intersect. And when I say never, I mean they will not usually intersect. you'll see an example or two where they want to take a moment right now and just talk about another capital of the world. That's Vienna, Austria. If you've ever been there, that's awesome. I've never been there, but one of my favorite movies is set there. It's called Amadeus. So that's your audio check, Vienna, Austria. Anyway, we've got to define the word asymptotes. What are asymptotes? They are lines to which the graphs will always get closer, and they're represented almost always by dotted lines. So you can see here's the dotted line, that's the asymptote, and the graph that we're graphing, this function, will always get closer to this asymptote. The further down you go, the closer you get. The further up you go, the closer you get. As the graph approaches from the left, as x approaches 3, we can see that the graph will get closer to the asymptote. And from the right, you can say as x approaches 3 from the right over here, we can see that it gets closer and closer to the asymptote, but never actually touches it. You can get as close as you want to the asymptote simply by going as high or as low on the graph as you need to positive or negative infinity. Here are some other examples. So you can see, in general, you can say things like as f of x approaches infinity as x approaches negative a. Here it would look like this. F of x approaches negative infinity as x approaches a from the negative side. F of x approaches infinity as x approaches a from the positive side. And f of x approaches negative infinity as x approaches a from the positive side. Those are that's how you can say those things when you're dealing with vertical asymptotes. Numerically, this is what it looks like. As x approaches 3, you can see we started at x equals 2, 2.5, getting closer and closer to 3. As x approaches 3, f of x will approach negative infinity. You can see how incredibly large or how negative this function gets as x approaches 3. That's basically following the graph down here. The closer you get to 3, the lower down you go on the graph. Same thing here. As x approaches 3 from the positive side, then f of x gets larger and larger and larger, approaching positive infinity. So if they ask you to find where the vertical asymptotes are, you simply have to figure out where the denominator is equal to 0. So you don't even need the numerator for this. You just figure out what the denominator is equal to 0, and you can say, well, you factor it, for example, and you get x equals negative 4 or x equals positive 2. And here they are. I've even highlighted them. You could see x equals negative 4 would be right here, and x equals positive 2 would be right here. If you're strictly being asked to find the vertical asymptotes, you don't need to graph it. You just need to list them, and this would be a good enough answer. I'm just showing you where they are on the graph here. Here, there's a little bit of simplifying you can do. If you factor out an x, you get x over x here, and they cancel, and you get x minus 4 over x squared minus 1. This function is equivalent to this function except where x is equal to 0. You can't let x equal 0 here because it used to be in the denominator. So although the other two, x equals plus or minus 1, do create zeros in the denominator for this, and they create the yellow and the green asymptotes, the x equals 0 creates this hole. And that's because you can simplify it out. You can factor out an x from both the numerator and denominator, and they cancel. But still, if you were to plug in 0 into the original, you would get an undefined value, which is why that's right here. That's that hole. The asymptotes still are x equals plus or minus 1 only. Here, you can set the denominator equal to 0, solve, and you get these 3 values, and each of the 3 values gives you an asymptote. x equals 0, the blue one, and then plus or minus square root of 5. That's the assignment. I'd like you to start for E1, copy the problem list in your composition book, and do the first problem, and I'll see you in class.